we're going to get into the technical stuff and the deep. So please, Adam.
Okay, let's see. Is it better if I hit a light? Let me just try it and see. Nah, too dark, right? All right. I can dim it just a little? No? All right. I think that seemed too dark, so you all fall asleep. Anyway, it's nice to be here, give a second talk. This one will be a little more technical. I'm going to tell you about recent progress in measuring the expansion rate of the universe, the Hubble constant, through observations of Cepheids, parallax, geometry, and how it may be telling us that there may be something else going on in the universe. And if anybody wants to follow later some of the details, a lot of what I'm going to talk about is in this most recent publication from just a few months ago. Okay, well, Marilyn did a great job of setting out what it is that we do in cosmology, but I'm just going to give my sort of very brief version that one of the only ways we can learn about the composition, age, and fate of the universe is by watching the universe expand and measuring it, doing that around us. So we assume that the universe follows general relativity, that it's homogeneous and isotropic on large scales. We test these things. And from that, we can derive this equation of motion for the universe, how the scale factor A that you see here on the grid, how that changes with time. And this equation of motion, well known as the Friedmann equation, it's over here on the right. And so on the left-hand side is the observed property of the universe, its expansion, change in A with T. On the right-hand side is all the interesting stuff that we'd like to know about the universe, the sources and sinks, the different matter and energy densities that cause these changes to the expansion of the universe. And so ideally, we would just go out as cosmologists and measure A of T, and we would learn everything we wanted to know. Now, we can't directly observe A or T, but we observe proxies for these. Instead of A, we observe redshift. That's very closely related, just the inverse. Instead of time, we measure distance. And knowing the speed of light, that tells us time. And of course, distance is the most challenging thing to measure. And so I'm going to talk about that coming right up. Now, it turns out, at least when we thought the universe was simple, was just matter dominated, that really just measuring the first two derivatives of A would tell you most of what you wanted to know. And so that's why cosmology used to be called the quest for two numbers, because in just a matter dominated universe, the first derivative of A dot, the Hubble constant, sets the size scale, the age scale for the universe. Back decades ago, there was a lot of disagreement by about a factor of 2 whether we lived in a 20 gig-a-year-old, very large, slowly expanding universe, or whether we lived in a small but quickly expanding universe with a large Hubble constant. Through work, particularly with the Hubble Space Telescope, by early 2000, this was known to about 10% precision. The second derivative of A, was defined as the deceleration parameter, the expectation that the expansion would be decelerating because if you have just a matter-dominated universe, that's all that can happen. But it would still be very interesting to actually measure the deceleration parameter and equate that to the actual mass density of the universe. Even as late as the mid-1990s, when astronomers were only finding omega matter of 0.3, theorists were saying, surely there is more out there. Go and look on larger and larger scales. And so that is what you can do by actually measuring the effect of omega matter on the entire expansion rate of the universe. It's also could test the geometry of the universe. Could we find that missing 70%? Tell us about the fate of the universe, about the origin, the viability of inflation, really, really big questions like that. So the 1990s, at least in my mind, an experience, was a very special time for going after these kinds of measurements. These questions had been around for decades, but in the 1990s, some truly long-range standard candles became available. So I'm going to talk about, these are the two primary kinds of standard candles I'm going to talk about in this talk. On the left, well, both of these are very bright, and they're very good for measuring long-range relative distances. So on the left, of course, are the Type 1a supernovae. These are exploding white dwarf stars that have reached at or near the Chandrasekhar limit, and they give you a very uniform explosion. We believe they live in binary systems, and mass is transferred over either by accretion or by stellar winds or overflowing of Roche lobe. And so these give you a very uniform explosion. I'll say more about that in a little bit. These are rare, only 1 per century in a galaxy, which is why we can't just use these. There are not very many very nearby. But they reach billions of solar luminosities. The others go back even further. These are Cepheids. These are supergiant stars which pulsate. There's an instability which causes them to oscillate, and the time scale of their oscillation relates very closely to their density and their total mass, and hence their luminosity. So empirically speaking, there's a very tight correlation between the period at which they oscillate and their luminosity. That's very clear from pulsation theory. Now, these are much more common, and so we could find these in many galaxies if we want, and these reach hundreds of thousands of solar luminosities. Okay, now of course why we love standard candles is they are one of the best ways we have for measuring distances. Of course, the inverse square law relates the brightness to the distance. But there are complications. Sometimes we encounter standard candles. We think they're standard. They're not actually all the same. And so a lot of effort is done by astronomers to sometimes standardize what start out as fairly close to standard candles, but not perfect. Another complexity is dust that appears in galaxies, primarily interstellar dust, which does dim the light of standard candles, makes you think they're further away. However, it also tends to shift the colors. Most dust we're familiar with has well-known ratios between how much dimming per how much color shifting. And so by knowing what the colors ought to be, we can account for the amount of dust and sort all of these things out. So as I said, the 1990s was kind of a special time, particularly for the Type 1a supernovae, when a lot of work was done to empirically standardize the Type 1a supernovae better than they come to us in nature. There's a good correlation between the rate at which the explosion decays and the true luminosity that's determined empirically but understood from theory. And of course, these kinds of corrections for dust really sharpen these tools up. So by the early 1990s, there were one particularly important sample, the Calantololo sample, collected from Chile, that collected about a 20 Type 1a supernovae out into the Hubble flow and really started delineating very sharply the expansion of the universe. I mean, people had seen the expansion of the universe for decades, but not with this kind of precision. And so that was in the south. In the north, I collected for my own thesis about 20-some objects, the data points you see in red. And so between these two samples, you had really a sharp delineation of the expansion rate, individual distances that were good to about 6%, a demonstration that expansion locally is linear, and this made use of tools, as I said, were not previously available, like CCDs and these various corrections that sharpen up these standard candles. Now, although we could measure relative distances to about 6%, the ability to measure absolute distances, to actually calibrate the true luminosity of a supernova, kind of lagged behind. And that's what you need to be able to measure the Hubble constant. You actually have to say what the absolute distance is. And so here's a little primer for string theorists. When astronomers often like to use the unit of a magnitude, and a magnitude is just, you could think of it as just simply the logarithm of the distance. And the particular scale that we use, 5 ticks, 5 magnitudes on this scale is truly about a factor of 100 magnitudes, factor of 10 in distance. Now you understand magnitudes. Now, as I said, the trick, though, was to be able to get an absolute distance and actually measure the Hubble constant that right now here is added to the logarithmic distance. And I'm going to talk more about that later in the talk. It just so happens that the ability to do this actually came later in many ways than the ability to measure the second derivative of A, the deceleration parameter. Okay, so most of you know this, by the mid-1990s, 2 teams, I was a member of one of them, set out to compare nearby Type 1a supernovae to much more distant ones, typically at about a redshift of 0.5, much fainter. And we're shocked to see that after you subtracted off a kind of low-mass universe with no cosmological constant, that the supernovae were fainter. implying that something like a cosmological constant was needed to fit these data. In other words, the universe was accelerating. And after a fair bit of analysis, both teams concluded that this was indeed the result. Now, a niggling worry that we all had at the time was, what if there was something else that was dimming the supernovae at redshift 0.5, not distance, but some kind of gray dust between the galaxies, or that, I say gray dust, larger dust grains that did not shift the color of the light, just dimmed, or alternatively, if the supernovae were just born fainter and were getting brighter with cosmic time. Theorists can be very mean at these times, and they come up with all these crazy ideas, and you have to kind of actually address them all. But we realized that was very important to do. So the interesting thing here was that if there was some kind of astrophysical, not cosmological dimming of the supernovae, then presumably as you went to higher and higher redshift, that would just continue. Whereas what cosmology tells us is if the universe is truly dominated by lambda or something like it now, you go back far enough and it must have been dominated by dark matter. Structure grew, attractive gravity was the dominant form. So the real right answer does actually turn over in this relative Hubble diagram. These supernovae will be brighter than these. And so by going out even further, we hope to see this turnover, or see if we had been following some continuous dimming curve. At the same time, over the next 10 years, there were many ground-based surveys that collected much larger samples of supernovae. So fast forward 10 years, right, and the Hubble diagram is extremely well populated with over 1,000 type 1a supernovae. And now that we're binning the data, you could see, and particularly by going out very far with the Hubble Space Telescope, we were able to see this turnover, and were convinced that we were not being fooled by some kind of gray dust or astrophysical dimming or anything like that. And in fact, the particular shape of this does look like lambda to about 10%. The equation of state looks very much like lambda. And so that was pretty much where we were. And it's interesting to compare my first graduate student, Dan Skolnick, who's put together the largest sample of well-calibrated supernova data called the Pantheon sample that lots of people are using. When he actually fits now in the omega matter, omega lambda plane, the constraints from the Pantheon sample, you get a contour like this. This was our original discovery contour, so obviously, we had much less precision, but, we were not too far off the mark. And so, of course, though that's even just from supernovae, about 6 sigma evidence for dark energy via acceleration. Once you bring in data from the cosmic microwave background, baryon acoustic oscillations, the evidence goes way, way, way up, which is why we all believe in dark energy or something like it as what's going on. Okay, so of course this is all prologue to questions like, what is actually causing the acceleration? And I mentioned this last night in my public talk. I don't think these are surprises to anybody, that we're either looking at something like vacuum energy, the unhappy marriage of an idea from particle theory that there should be vacuum energy, and general relativity, that vacuum energy should have gravitation that causes acceleration, and of course the terrible mismatch between the two, but nevertheless that remains a very important word idea, at least. Dynamical dark energy, so you have the potential energy of a field, which gives rise temporarily perhaps to something like this, but there are important tests of the distinction between these, whether in this case the equation of state is always -1 because it's a constant vacuum energy, or whether you actually get the chance to see a change in that would indicate that it is not. There's no guarantee how small or different the size will be, but it is possible that we could detect this. And of course, option 3 of general relativity on a length scale that we never have before without coming up with something like dark energy. So perhaps there's something funny going on there. And so here the important test is to see that the actual characteristics of dark energy as we measure them, the equation of state, itself depends on scale. That what you see, how you see it behave on the larger scales is different than smaller scales, which are better probed by the growth of structure. So having said all this, we don't know really for sure what's going on, but we can say that number 1 is very easy to calculate. And it has some preference for simplicity, but mostly I would say it's easy to calculate. And so easy to calculate is good because when you want to do an observational test, you can then calculate what your observational test should look like in Model 1. And so the way we play the game now is we assume plain vanilla lambda CDM, which is to say really option 1, and then we look for departures. We look to see, does that really fit the data? So if we now step back, this was all sort of pre-early 2000s. If we now step back, I can pose this sort of ultimate end-to-end test for cosmology. So after a century of cosmological research, we have a standard model, this vanilla or minimal lambda CDM. It has 6 parameters. It has a number of ansatz about the equation of state, n effective, omega k, which are tested. Of course, it's dominated by these dark components, 95% of the universe, with physics that we don't totally understand. However, we make some simplistic assumptions about those, and then we use this form of the model as it looked before recombination to predict the physical size of fluctuations in the plasma, including, most importantly, the sound horizon, but also omega baryon. Then we observe the angular size of those fluctuations, or we measure the deuterium abundance, the primordial, and that comparison between the angular, or the abundance, and the predictions allows us to calibrate the free parameters in the model, and in some cases test the ansatz as well. Once calibrated, we then use this form of the model, which is quite evolved from the previous form, to predict the expansion history of the universe. And along the way, we get guardrails. We get baryon acoustic oscillations and supernovae. They're guardrails because they don't tell us we're on the right road. They don't tell us we have all the right parameters, but they make sure we sort of don't go off curves in the road, that there isn't some very surprising behavior later on. And finally, what comes out is a prediction of the expansion rate, the Hubble constant today, 67.4 plus or minus 0.5. So a very powerful test of this whole story is to actually measure the Hubble constant at comparable precision, which is exactly what we would like to do. So we started a project to do this a little more than 10 years ago. We thought we were doing something slightly different. We thought we were measuring the equation of state by combining with the CMB, but it's very closely related. And we thought we could build a measurement chain to measure the Hubble constant to hopefully approach 1% precision. And the way we sought to do this was to take the best tools that were available at the time, and I think they still are, which is to use geometry, and I'll talk about that. We do that multiple ways, to calibrate the true luminosity of those Cepheids, and then to look in galaxies that host both Cepheids and Type 1a supernovae to calibrate them, and then they go all the way out into the Hubble flow and tell us how fast the universe is expanding. Now, how would we do this better than people before? Well, we saw a number of ways that we could reduce systematics in the measurements themselves along the chain, and I'll describe how that is, as well as by making the observations in the near infrared to avoid dust, which has always been a problem for astronomers. Also, we thought we could thoroughly propagate the errors, systematic and statistical, in ways that in previous generations people hadn't always kept track of. Okay, so here is basically the ladder I'm going to walk you along, and you could think of it as measuring geometrically, for example, here illustrating parallax, distances on scales like a kiloparsec, but sometimes we go out a little further than that, to calibrate the luminosity of Cepheids. And then in this intermediate range at megaparsecs, where there are both supernovae and Cepheids. And let me say this right up front. I see people get confused about this step all the time. These objects, these Cepheids and supernovae, are assumed to be co-located, not used. I see papers all the time arguing about how small these redshifts must be and what big errors there must result from this, and it doesn't matter what the redshifts of these are. The only principle here is of co-location, the fact that these two things are in the same place, and so when you measure the distance to one, you measure it to the other. This has nothing to do with cosmology. But then finally, cosmology enters here. These are the Type 1a supernovae out into the Hubble flow, and of course they tell us how fast the universe is expanding once calibrated. All right, so I'm going to walk you through some pieces of this so you get a feel for what the measurements look like and what the process is. I'm going to start out with parallax because in many ways it's the simplest, and actually there's been the most progress in parallax over the last, I would say, 5 years or so. So let me tell you about parallax. I know I'm not making fun of string theorists, but I know you don't think about parallax very much. So, in Astro 101, parallax is very simple, right? The Earth goes around the sun, and when you look at a distant object like a star, it moves back and forth. Because of that movement, you measure that angle, and as long as you know the astronomical unit, which we do to very high precision, then what could be simpler? It's not physics, it's just geometry, okay? However, the problem is parallaxes are small because stars are very, very far away. Okay, so here is the nearest star as observed with the Hubble Space Telescope, highest resolution telescope. And if you look over the course of a few years, well, you see two kinds of motion. One of them is just a drifting motion that all stars have. And then on top of that, superimposed is the parallax motion that you want to try to measure. And so just to show you, right, these are really small motions. Whatever motion you see perpendicular to the drifting motion is what is due only to parallax. As far as I know, this animation right here is the only parallax you can see with your naked eye that anybody has ever seen. Because after that, it becomes statistical measurements because it becomes harder, at least that you can't see it with your naked eye. That's really what I wanted to see. So in practice, most of the stars we are interested in are thousands of times farther away, okay? And of course, parallax goes down as 1 over the distance. So when you are interested in the parallax of, for example, Cepheids, which are not every star is a Cepheid, they're fairly uncommon, so you have to go out kiloparsecs in the Milky Way to find them, then you are measuring parallaxes which are more like milli-arc seconds. And in particular, if you want to measure a parallax, and this would be typical of what we want to measure, 3 kiloparsecs, then that star will move back and forth 1/100th of a single pixel on the Hubble Space Telescope. And you want to measure that well, right? So, that sounds pretty daunting. However, my colleagues and I came up with kind of a cute idea a number of years ago of just how to do this, which is ordinarily we are measuring or we are imaging one star and comparing it to another star, let's say every 6 months. Imagine one of these stars is infinitely far away. It's not, but quite far away. Then you are limited ultimately in measuring this 1/100th of a pixel by how well you could centroid the star. Where is that star actually? It involves many pixels, but what is to a subpixel, what is the location? Well, you could kind of fit this function. We call it a point spread function. And our precision of actually doing that happens to be 1/100th of a pixel, which is not good enough, therefore. So the cute idea we had a few years ago is instead of taking an image like this, like you normally do, instead spatially scan the telescope along one axis so that you are essentially repeating this measurement over and over and over thousands of pixels in the other direction. That is, you're beating down the errors through sampling. And so if you're a little confused about what I'm talking about, here's a tiny little movie, but literally the stars go flying by, and you're comparing pixel by pixel their separation. And obviously you could get much greater precision because you have much greater sampling. And here's a tiny patch of one of these images with the spatial scanning. We actually are just getting a higher information density on our images, where we are lighting up 30% of the pixels instead of 2% of the pixels. And when we do this, and now here I am extracting scan line by scan line, those scans of individual stars on one frame, aligning them in time. One of the first things that really struck me was this kind of noise that you see. I was like, what is that? But you quickly recognize when you line up the stars, that noise is correlated. That is the jitter of the telescope. The telescope itself is bouncing along in one axis while it's scanning in the other axis. That's fine because I only care to measure separations or differences between stars. So you take two stars like these two blue ones and you subtract them and you get this very smooth line. So you remove the jitter and then you get to beat down the error over thousands of separate measures. So with this technique, that's an order of magnitude better than people were previously doing. Okay, so fast forward 4 years later, after using this technique and observing about 8 Milky Way Cepheids, each mark here is an observation separated by 6 months. We've subtracted off the proper motion. So this back and forth motion you see, that's just parallax. And 1 over that tells you the distance. So this was pretty cool and allowed us to get a 3% calibration of the luminosity of Cepheids. Meanwhile, these spatial scans are also useful for measuring just the brightness of the Cepheid, which is part of the standard candle measurement. And so knowing that Gaia, a European Space Agency satellite, was planning on measuring parallaxes to comparable precision over the whole sky, we picked out 50 other Cepheids where we just measured the fluxes with HST using the spatial scanning and waited for Gaia to measure the parallaxes. And in 2018, they released data release 2 of those, which gave us another 3% calibration of the luminosity of Cepheids, independent of this technique. So in this case, we're measuring the parallaxes ourselves. Here, the European Space Agency, Gaia, is measuring them. We're just measuring the fluxes. So now, jumping ahead to where are we on calibrating the luminosity of Cepheids with parallaxes, there's now been 3 ways people have used. The fine guidance sensor on HST, which measures some of the nearest, shortest period Cepheids, and then these 2 techniques that I've talked about measuring more distant ones. And this is expected to improve quite a bit when Gaia Data Release 3 comes out. However, we are now spanning fully the period range that we see in supernova hosts, the next rung. And when Gaia reaches its final advertised precision in about 3 years or so, this step will be good to about 0.4% in the calibration of the luminosity of Cepheids on the same system that we are going to use later along the ladder. All right, now this is not the only way even to calibrate geometrically the luminosity of Cepheids. Parallaxes offer 3 ways to do this. Another way you may have heard about is these orbiting eclipsing binary systems in our nearest neighbor, the Large Magellanic Cloud, the LMC. These are called detached eclipsing binaries. And what basically happens is one star goes around the other star, and you measure the Doppler shift of the star orbiting the other star, and you measure the timing between the transits by the dimming. You see people do this for exoplanets all the time. That tells you the physical size of the star. You measure the angular size of the star using a relationship based on interferometry. So interferometry gives you angular sizes, and you calibrate through a relationship with that. An angular size and a linear size gives you a distance, and so that's been done to 1.2% now in the Large Magellanic Cloud with 20 systems. And then a third is this famous system of water masers orbiting NGC 4258. It's supermassive black hole, and so radio. Sorry.
Where does the size come from?
Yeah. So what they actually do is you measure, you look at red giants in the Milky Way and use interferometry to measure their actual angular size. And then you measure their colors or temperatures, and through the Planck law, there's a simple relationship then between temperature and surface brightness. And so if you have angular size and a brightness, then that relates to the surface brightness. So once they've calibrated that relationship, you could apply it to any other stars. I have some backup slides showing some of this. So basically, they're getting out the physical size of the star by calibrating it through interferometry. Because it's the same kind of star. That's right, red giant stars. They're very simple in that way. And then the masers, water masers, which orbit NGC 4258 in Keplerian motion. These have been tracked for 15 years and give a very precise distance to that system as well. So these are all the different calibrators that we can use. Okay, let me go on to step 2. Step 2, this is really, I got to say, one of the main reasons the Hubble Space Telescope was built, was to be able to resolve stars in other galaxies, and in particular to allow you to calibrate distances by recognizing those kinds of stars. And Cepheids are, top on that list. So this is the principle of co-location that I talked about. No cosmology, just the fact that a star explodes in this galaxy. We come back later with Hubble and observe Cepheids in that galaxy and calibrate it. The problem when Hubble was first launched was the camera. Well, the telescope was not so good. Then the cameras were actually kind of not up to current specs. So you can only do this out to about 20 megaparsecs, and there's only a handful of supernovae that close, the Field Camera 3. This doubled the range to about 40 megaparsecs that you could observe Cepheids. If you double the range, you increase the volume by a factor of 8, and that means there's a good one about every year or so. And so we've been able to reach out further now. We've calibrated 19 this way, and we're just in the process of finishing up 38. And that will be a complete sample at 0.011 in redshift, and that's just a very large sample. And we only pick modern, reliable supernova data to do this, observed the same way as ones in the Hubble flow. Okay, so here are the period luminosity relationships that we measure in the individual galaxies as observed in 3 bands, and then in these anchor galaxies, whether it's NGC 4258, the maser host, the Large Magellanic Cloud, or the Milky Way where we observe parallaxes. All right, one of the ways we've been able to reduce systematic errors over past approaches is, and this is really key, you want to use the same telescope when you observe your standard candles in 2 places along the distance ladder. Because if you use the same telescope and the same instrument, then you cancel out the flux calibration problem. The flux calibration problem has always been a big problem in cosmology. How many watts or how many ergs am I really getting from this source? And the answer is, who cares? If you use the same telescope at both steps, you cancel that. And so that, I think this is the first distance ladder approach that has actually done that successfully on all steps. So we use the Hubble Space Telescope to observe Cepheids in these supernova hosts, but we also use it to observe the Cepheids in the anchors, even though this is ridiculous to do because these are very bright. Usually you don't use the Hubble Space Telescope and waste its time on something very bright, but not for this problem. For this problem, you actually want to use the same telescope. So we observe Cepheids with the same instrument filters over the same range of metallicities and the same range of periods so that there are no systematic error lever arms coming in on this. Okay. Another big advantage over past measurements, and this is shown very nicely if these are Cepheids, their period luminosity relationship in the Large Magellanic Cloud. And here you see very well the advantages of observing in the near infrared. And so here are those same Cepheids, 70 of them in the optical, seen with HST. And by the time you go to the near infrared, or even with a small dereddening term, which everybody uses for even tiny bits of reddening, you see you get a very tight relationship, about 0.07 magnitude. So they really give you better distances because you reduce the systematics of extinction or metallicity dependence, things like that. Okay, so the third step is actually, it's easy only because we've been working for so many years collecting lots of supernovae, but this is just the Hubble diagram of type 1a supernovae. Now, in the past, we have measured this not too close because you don't want to be sensitive to local flows, the non-Hubble flow type motions, which could bias your answer. And you don't want to go too high in redshift, or you have to start bringing in cosmology. You have to start bringing in changes in the expansion rate due to omega, dark energy, and it's cleaner if you could deliver just a measurement that depends on the Hubble constant. So we generally use this sort of range as sort of the sweet spot for doing this and determine what the intercept is. And then finally, we do one simultaneous fit. It's kind of a multilinear regression using these different kinds of data. This is the distance ladder. Then the distance ladder is the simultaneous fit of those relationships with the various kinds of data, keeping track of the covariance between the data and the model and types of data that have covariance. At the end of the day, the determination of the Hubble constant is actually quite simple. It's just really the determination of 2 numbers, the absolute luminosity of a type 1a supernova and the intercept of its Hubble diagram. Here's the actual data we use, and this is sort of a visualization of it because I'm actually showing it rather than just the matrix form. But here is the place where geometry calibrates Cepheids, and this is done in 5 different kinds of sources. As I said, 4258, the Large Magellanic Cloud, and Milky Way parallaxes, which are individual, so they don't have one distance like the external things do. Here are the 19 galaxies where we both observe Cepheids and use them to calibrate the supernova that went off there, and here are the hundreds of supernovae out in the Hubble flow. So jumping to the answer, as of a few months ago, 74 plus or minus 1.4, a total uncertainty of 1.9%. I'll say more about the uncertainty in a minute. However, remembering what we saw earlier in the talk, the 67, the CMB plus lambda CDM, and this has been growing with time. Now, the first thing to look at as we start to think about systematics is these 5 different sources of the geometric calibration of Cepheid. So I have to say, more than 10 years ago, this was the hardest step far and away. This was the reason people struggled to measure the Hubble constant. The geometric step was very difficult and was poorly measured, okay? And it's gotten a lot better in the last 10 years. And so I'm just breaking out the answer we would get from each of these 5 different versions of this. Now, 3 of them use Milky Way parallaxes, but they're measured in such different ways that they really would have very different systematics from each other. And then most recently, the improved detached eclipsing binary distance to the LMC. These all give answers somewhere around 72 to 76. They're consistent with each other to about 1.3 sigma. If you're looking to solve the Hubble tension with your choice of favorite anchor, there's really nowhere to hide here, because this is not really giving you anything that you can really dig your teeth into for that. But, of course, that's not the only source of systematic. Just to give you some feel for how big an effect we're talking about, the difference between what we observe the Hubble constant to be locally and the Planck plus lambda CDM value is 0.2 of a magnitude. That's 20% in brightness. Okay, so looking at my 3-step distance ladder, and here are the residuals, that represents messing up one of these steps to about the level of these red dashed lines here. So obviously it's not in the cards for the statistics. And I have to say, I mean, as somebody who's been measuring photometry most of my life, 0.2 of a magnitude is really big. I mean, I worry a lot about 0.02 of a magnitude, but 0.2 of a magnitude, yikes. That's a big amount. Now, we looked at many variants of ways of doing the analysis. Even though we weren't that sensitive to them, we needed to consider them anyway. These are the things that people worried about in the past. Are we assuming the right kind of dust in these galaxies? How do we reject outliers? Not every blinking star you see is a Cepheid. Most of them are, but not all of them. What period range do you assume a linear relationship over? Is there a gradient or any dependence of metallicity in the host galaxy with the results you get? Do we use 2 slopes or 1 slope? Where do we start the Hubble flow? Which light curve fitter do we use for supernovae? There's one I developed for my thesis, MLCS, one that's more recent, SALT. What kinds of galaxies will we allow in our analyses? And I could say more about that if people know what the issue is. But basically, these have some variation, but it's not very big, and we propagate the variation due to this into our systematic error budget. But we haven't seen a form of analysis yet, and many people in the literature have tried varying all kinds of things and have not found one.
People have talked about the difference in metallicity between galaxies that host the Cepheids and the typical galaxy that hosts supernovas.
Right, so there's not much difference, and we know this because we measured the metallicities of the host galaxies, 4258, the Milky Way. Only the LMC has a somewhat lower metallicity, but all of our supernova hosts, the Milky Way and 4258, are all typical big spiral metal-rich galaxies. And we measure this with nebular lines, and we measure it as a function of radius using H2 regions, and we index the Cepheid to the radius that we find it.
So what's the,
So it's about, the whole range would be maybe 0.2 dex, and we fit it, though, when we're, yeah.
Is that propagated as an error, the metallicity?
It is, because it's a formal term. If I go back, right, the formal term in our fit is actually, here we go. The formal term in our fit is actually the metallicity dependence of the relationship, and in here are in the data matrix here are the metallicity measures.
What about the metallicity of supernova?
Nobody's ever found a relationship with supernovae and metallicity. However, this gets into this other question, which is that. So in Cepheid, the Cepheid hosts are all spiral galaxies. They have to be. So we could, even though nobody's ever seen a relationship of metallicity, we can limit our analysis in the Hubble flow to only spiral galaxies or only star-forming galaxies. This only cuts 1/3 of the supernovae out because the ellipticals, those are rarer, and it has no impact on the Hubble constant. I mean, it's a good thing to do.
How much does it change the error?
Negligible, because the error is, you're taking 300 objects here and you're cutting it down to maybe 200, where statistics of 19, 200 is not going to change things. So this whole contribution here to the error is 0.5% in quadrature. So changing that a little bit doesn't matter. But that's a good question. They are young stars. They are they are massive stars, and only young galaxies are still forming new massive stars. Elliptical galaxies are what we call red and dead. They have had a big burst of star formation billions of years ago, and now it's just a bunch of stars that are later in their lives. Okay, so this is a sort of detailed breakout of our error budget as it has been over the last 15 years. And so we have about 10 categories of uncertainty that we track: the absolute scale, the Cepheid colors, the period luminosity mean in the anchor versus in the individual galaxies, the Cepheid metallicity. This is what you were asking about, David. This, if you could kind of see this bluish term, this is how this bluish term has changed over time. It can change depending on what we're using as anchors. What's interesting to note is, the uncertainties have been going down. The actual value of the Hubble constant has not been changing very much. Back in the day of the Key project, it was 72 to 74. Here, 74, 73.8, 73.2, 73.8, 74. We're bouncing between around, it could be as low as 72 or as high as 74. But it's been very stable while the uncertainties have come down. The main improvements since 2016 have mostly been with the anchors. The Milky Way parallaxes that I talked about, the better detached eclipsing binary distance to the LMC, better matching of photometry. I'm going to describe that in a second. We've been able to calibrate something, a count rate non-linearity term in wide field camera 3, that if you're going to compare brightnesses, you have to really understand well. So, big question, of course, is how does this exactly compare to the CMB? Well, let me just back up a little bit to 2016. 2016 is when we published our result that really, for the first time, was in major tension, not just minor tension, with the Planck value. And then lots of people started reanalyzing this data. There was Bayesian, hierarchical, reanalyzing, sophisticated outlier analyses. There was an analysis by the Planck team members changing the reddening law in each individual galaxy, which you might thought would blow up the errors, but it didn't very much. This was done by... It is now a problem set in Joe Bovey's class, in his astrostatistics class. So, if you want to reanalyze this, get some credit at least towards your PhD with Joe Bovey. And the right answer in his class is 74 from this data. So I think once it's literally a homework exercise, I think we could think, okay, this is probably the result you're supposed to get from this data set, independent of what you think of the data set. Now, then people started looking at what if you use near-infrared supernova-like curves. I talked about near-infrared Cepheid data. There's not many type 1a supernova-like curves in the near-infrared, but they may have lower dust, and so that could be a good thing. That didn't change things very much. The Carnegie supernova group did this as well. Then the Gaia parallaxes became available. Our own HST parallaxes became available. Nothing changed very much. And then with the new Large Magellanic Cloud detached eclipsing binary results, that's where we are. Meanwhile, if you were even thinking about concern on the Planck side, I'm not very concerned from the early universe side, because there are so many independent, they're not independent routes, but independent data that you can use. Basically, if you start with any CMB data set, WMAP, ACT, SPT pole, once you bring in baryon acoustic oscillations, the constraints tighten down quite impressively in the range of 67 to 68. It could be as high as 68 and a quarter or something like that. But with using CMB to calibrate BAO, that's what happens. Now, alternatively, completely independently, as I talked about, you can use measurements of deuterium abundance to constrain omega baryon, which helps constrain the sound horizon and calibrates essentially the cosmological model. So then you have the information you need to calibrate BAO. That gives a very similar answer as well. If you hear anybody talk about an inverse distance ladder, what they're generally saying is if they assume what the sound horizon is, which usually means that they used the CMB or they've used this deuterium abundance route, then they built a ladder in the other direction. So the hard dividing line here really is, did you calibrate your absolute method in the late universe or in early universe physics? I still know people get confused about this. One fair question to ask is, do you have to assume anything about the number of neutrinos? If you do, you're on the early side. If you are like, what? You're on the late side. So
in the late universe calibration of lambda, the relationship between distance and luminosity.
So what's your question?
When you have negative curvature, then the luminosity falls off faster than it would.
Correct.
Right. So is that the main way that you would measure when you're talking about recent the recent regime in the observed universe?
No, what I'm talking about is building. What I'm talking about is starting out by measuring geometrically distances in the very local in the Milky Way, and then using that to calibrate things that really don't go out much further than 0.05, where effects of curvature and things like that are really irrelevant. And that this is a much bigger effect than that. In fact, just to give you a feel for it, right? When people talk about what could be going on, right? This is meant to be more cartoonish than too realistic. But we talk about what if dark energy was not lambda? Well, you can't do too much of that because, as I said, baryon acoustic oscillations and supernovae are like these guardrails. They are not letting you do too much. If you want to push it at 2 sigma, you could get you could change the equation of state by 0.08, or you could change the derivative by 0.8, and that'll get you about the length of this arrow, maybe half of it. Not very satisfying. And effective, you could increase that again at 2 sigma by about 0.4, maybe get you some of the way there. I don't know. Not, maybe better than dark energy, but not so effective. Curvature, and this is what you're asking about. So, 0.01 probably really pushes it, and already that's not nearly enough. More interesting, I've seen some papers on dark matter interactions people may talk about in the early universe. Both of these operate in early dark energy. This would be at redshift of 10,000 to have a short episode of a scalar field that injects energy. It injects energy, it expands the universe faster, which makes the universe become transparent earlier, which makes the sound horizon smaller. And so these operate, and I will say, people are mostly barking up the tree of the sound horizon these days because that seems the place where you might be able to do something, because all of these things on the left at some level depend on the sound horizon or affect the calibration of the sound horizon. Okay, a question I'm asked all the time: do we live in a giant void that explains this? And the answer is no. Now, we're talking, it has to be about 9% in the Hubble constant. Now, we have 2 ways that we could say it can't be more, that the uncertainty in the local voidiness is about 0.6 or 0.4%. There's the theoretical way that many people have done, which is they've done very sophisticated n-body simulations of large-scale structure. They vary the location of the observer. They vary, then they define how the measurement is made, and they measure variations from large-scale structure of about 0.4%. So anytime somebody says, I'm going to do it this way, they're talking about a 15 or 20 sigma fluctuation. I mean, we heard the talk this morning. I mean, we assume we don't live in that special a place, okay, let alone near the center of it. Otherwise, you generate a giant dipole in the CMB. However, we can also do this empirically. If there is a void that we are living in, supernovae go all the way out to redshift 1 or 2, so you ought to be able to see the signature of that as a kind of inflection. And so with a student, Darcy Kenworthy and Dan Skolnick, we looked at variations in the Hubble constant as a function of where you do the split between what is inside and outside the void. And indeed, the variations really are of the sort of theory predicted side. And when there's been specific papers saying, well, they have some evidence from some galaxy survey in some direction that we live in a giant void, and we can rule that out at about 4 to 5 sigma. And that's not nearly big enough for Planck, right? I mean, to get up to Planck, we need a 9% void. And so it's just not, it would violate the Hubble diagram of supernovae, which looks very smooth, and it would violate what you would expect from large-scale structure. That's just sort of the bottom line with that, unless somebody has some other idea. I'm still going to keep seeing papers about this, but this is the number one reason that people think is the explanation.
It also would violate the KSE constraints.
Right. But as I said, for whatever reason, you stop a random cosmologist on the street and ask what is going on, they'll say, we probably live in a giant void. So It's just, I judge this because it's the questions I get at the end of every talk, and it's the papers I see new ones like every day. So just, you should know, we don't live in a void that big. We can live in a little void, but not that big. Okay. This is a really technical point, but this is a technical talk. You can't measure a distance ladder to this precision with the same detector unless you can prove that you can get linear measurements of flux over a very wide dynamic range. And so this is one of my job, calibration ladder. It's knowledge of what the true relative brightnesses are of certain objects in the near infrared. You can often do this because CCDs overlap in the near infrared around a micron, 1.1 micron, so you get a sequence of things, and then you measure their brightnesses in the near infrared. And earlier generations of near infrared detectors had pretty big nonlinearities, like NICMOS, but we've calibrated, there's only about a 0.3% nonlinearity, and even the uncertainty in that is small enough. Here are the nonlinearity measurements over a range of, it's about a factor of 1 million in flux that we have done this, about 22 magnitudes. And so if you take the uncertainty in our nonlinearity, it propagates to about 0.3% in the Hubble constant. This is new as of about a year or so. So the answer is yes, the flux scale of this detector on Hubble in the near infrared really can, once calibrated, support a 1% measurement of the Hubble constant. Okay. The big one, right, is the unknown systematics. You've looked at everything I did and maybe everything looked okay, but gosh, I don't know. Something's got to be going wrong. This was the status as of a few weeks ago, okay? These are just two representative. This is from the Holy Cow team. Here are two of those representative early universe measurements. Here was our measurement. And then 2 weeks ago, team Holy Cow, which is measuring time delays in images of quasars with foreground mass. Now, they are measuring multiple image quasars. Some cases they're quads, 4 images. In other cases they're 2 images. In some cases they're long delays, short delays. They've obtained their images, which are the real key to modeling this, with the Hubble Space Telescope, but they've also done it now with adaptive optics. And they get very consistent answers across quads, doubles, HST, adaptive optics, different ways of doing the mass modeling. It's very impressive work. I mean, I've watched them do this now for quite a number of years. And independently of everything that I've mentioned, no supernovae, Cepheids, geometry, this is what they get. It's a late time universe measurement, 73.3 plus or minus 1.7. So their statement in their paper was that they can combine these two things in the naive way, and this would be 5.3 sigma apart. Now, we had a big conference a couple weeks ago where lots of other teams were coming out with their sort of latest results, and so now I throw a bunch of those here, okay? And so these were new measurements of masers from the CFA group that had measured 4258. They've now measured 4 systems tracked over 10 years. So this is just pure geometry, no distance ladder, just straight out into the Hubble flow. This is what they get. This was a group from Carnegie measuring tip of the red giant branch in lieu of Cepheids to connect geometry and supernovae. And these are Miras, which are other kinds of variables, an older population of star, that you could use instead of tip of the red giant branch or Cepheids to connect geometry and supernovae. So all 3 of these have some overlap in what they're using. And then something called surface brightness fluctuations, which is a statistical property that galaxies look smoother the further away they are, and you can use that to measure distances. So at the meeting, everybody was all excited at looking at this, right, and doing various data combinations. So this was our summary plot. If you just naively added everything together, which you shouldn't do, but then you would be at about 6 sigma. If you did something that was too conservative, I would say, because you're throwing out lots of data, you could say, I don't know how to sort these yet. I'll only use one of these at a time with the others. So if you only use Cepheids, those are our measurements, then you'd be at 5.8 sigma. If you threw away Cepheids, please don't do that, and Miras, then you would be at 4 sigma with tip of the red giant branch. Or if you use Miras and you threw away TRGB or Cepheids, you'd be at 4.4 sigma. The right thing to do, of course, is to combine these, just keeping track of the covariance between data in common, and you're going to end up being somewhere in between 6 sigma and in between the average of these. You're going to be around 5 sigma or something. Now, here's some late-breaking news. A paper that appeared last night on the archive from a postdoc of mine. We spent a couple weeks figuring out something looked funny here with this, and I don't just mean the location of the data point. We were more familiar. They had estimated this team, the data looked fine. It was the calibration that they had done of tip of the red giant branch. You observe this feature called tip of the red giant branch with HST in the halos of distant galaxies that host Type 1a supernovae. That's great, but then you have to calibrate it somewhere. They calibrate it in the Large Magellanic Cloud where there's a lot of dust in front of the tip of the red giant branch. And when I looked at it, they had estimated more dust than anybody had ever estimated for, and that clearing away was causing Wenlong Wan really dug into this, and what we found was the data that they had done this calibration on was ground-based data from like 25 or 30 years ago, sort of in the earlier days of CCDs, and it was a very low resolution. And so it produced what we call blending bias. It means that when the data is of such low resolution and it's a crowded region, stars merge into the aperture of other stars and start making everything look brighter. I have some backup slides I could explain this. So the paper showed if you replace the blended data with unblended data, then this is what you would actually get, everything else being exactly the same.
Would you have analyzed it if they got the value of 76?
I don't know. I think we're all Bayesians. We all look at stuff and go, that isn't what I expected, and then we look harder at something. If somebody gets exactly what I expect, do I also look harder? I mean, I wish I had that much time where I looked at everything equally hard.
I looked at the holy cow.
Yeah.
Right, and I don't,
Yeah.
They assume that the velocities are isotropic.
Mm-hmm.
Right, there's a lens sheet degeneracy.
Right.
And they use the same model for all of their systems.
Mm-hmm.
And there's no reason, doesn't mean their central value is wrong.
Right.
But I think that's one where, had Holy Cow gotten 66 or 80, then we would have worried a lot about the lens model.
So I would not have reanalyzed Holy Cow because I don't know how to do that. See, this was in my wheelhouse to actually look at this.
I just remember too well Paul Schechter going around giving talks.
So I learned about that. Right. So here was the problem with Paul Schechter's stuff. They showed this really nicely. You should have seen Paul Schechter's images were like the exact same quasar, and it was like 4 blocky pixels, 4 blocky pixels, 4 blocky pixels, and he was producing a lens model. The images that the Holy Cow team have thousands of pixels. It's like the spatial scanning stuff I was showing. They have so much more information. It's remarkable. So I take it seriously. I'm not saying that I know that they have the right answer, but I'm saying, it has nothing to do with many of these other measurements. So it's quite remarkable.
I mean, I just talked with some of our people who are
Yeah.
It's something where,
Somebody should reanalyze it. Yeah, right. I'm just saying the answer to the Paul Schechter thing is the data quality is an order of magnitude better than what Paul was working with.
And the problem was with his model.
Yes.
He assumed
Right.
isothermal sphere for dark matter.
Right.
And didn't
Right.
propagate the
Right.
model.
And also, when you find something like the data being blended, and this is very easy because you just compare it to the HST data, you go, this data is bad. It's not it's once you recognize that, you have to correct for it. Now, you're right, most of us just look at the things we're familiar with and you go, I know how to do this in about 2 days of work. I don't know how to do this in 2 years of work. So, hopefully everybody is jumping on all these things. I will tell you this about, we're sort of talking about confirmation bias. I'll tell you, this is my opinion. I'm interested to see what David thinks about this. People strongly believe that the late measurement should match this. And so the confirmation bias is really to get something over here. I mean, people push back pretty hard on the fact that this is not matching this. And so, I think in a way, this demonstrates our community works pretty well in that, we actually do the measurements. For the most part, we're more signal than preference. But, it's fair enough. You have to be very careful. I will tell you about the Holy Cow team. They're very proud of the fact that all their analyses are totally blinded. So they don't make choices about models and then look at this. But anyway, here I am reporting, let's put it this way. If the right answer is here and if we keep measuring it, we're just going to converge to it. Who's measuring on the other side here? Everybody in the late universe is measuring higher. And we could argue whether the right answer locally is 71 or 75, but I don't see how we get to 67 if people keep measuring a higher number than this. So anyway, so formally we're at about 5 sigma with many things that are totally independent here. The masers were really quite impressive. That has nothing to do with any of the steps that I talked about. Okay, well, we're doing our part to try to get higher precision. So as I said, we're right now this year with HST, we're in the process of doubling our sample. Right now, we're just observing objects number 32 and 33. I think we have 3 to go, and then we'll be at 38. That'll be doubled the sample. We will never double this sample again. Because there aren't that many supernovae out there. So, that's important, that we are really reaching the limits of what we can measure. And I'd say 1% is a reach, maybe more like 1.3%. But here's some period luminosity relationships in the next couple of years. So I showed you our progress up until this point. We have 2 big improvements that we expect in the next year or so. The doubling of the supernova sample, and when Gaia Data Release 3 comes out, these should occur in the next year. That will get our approach to about 1.3%, and that's about as well as we know how to do. LIGO is excited to measure the Hubble constant using these kilonova double neutron star systems, using those as standard candles. The big question here is really about the rate of these objects. I mean, they had one in 2017, and then they started writing templates for AppJ papers for, measuring the Hubble constant to incredible precision next year, and more power to them. But what we just don't know is how many objects per year are they really going to find, because it's hard based on one object to guess a rate. And so all I know is it's been 2 years and there's not been another one yet, but hopefully they will find more. Meanwhile, great projects like DESI, LSST, WFIRST, and Euclid, what are they going to contribute? Well, they're going to measure H of Z in the late universe. They're going to constrain W of Z. And so what I called these guardrails before are going to become tighter and tighter. And so any questions of can you do it in the late universe are going to be, I think, answered by those missions, if you can do this in the late universe. Right now it's looking a little rough, and it's either going to get much rougher or they will discover something important, and we go, oh, okay, we were missing that. And then there are new CMB experiments, lots of them, Simon's Observatory, S4, even some of the B-mode projects could potentially detect the signatures that are predicted by some of these early dark energy models. I don't know if David's going to go into that at all. But some of these specific early dark energy models have additional features that should be detectable. So I think this is an interesting story to stay tuned to, because it is interesting. Okay, yes, right. I had a couple final thoughts. I'm almost done here. Final thoughts. Final thought one is, it's always dangerous to go back to any historical anecdote to tell you what's going on. So I'm going to do exactly that. But, when we measured Q naught 20 years ago, it was about the same size effect, about 0.2 of a magnitude, quarter of a magnitude. And that was much harder, intrinsically harder, because you're comparing supernovae at redshift of, 0.05 or so, what we call the rest frame, out to 0.5, which is not the rest frame, different band passes, so you have to do these cross-calibration issues, something called K-corrections, which astronomers know, or physicists know as relativistic corrections, lots of terms that go as 1 plus z that depend on the spectrum of the object you're looking at, very tricky. And of course, evolution. What if those supernovae really were different back then? And so that was a much harder problem. And so this is what we were comparing, data over this range. The much easier problem is what we're doing now, which is comparing from redshift 0 to redshift 0.05. The whole thing is done in the rest frame. We never change filters. We never change detectors or instruments. There's no evolution to worry about. There's no K-corrections of any reasonable size. And yet the size of the effect is the same. So some days I sort of chuckle about this, thinking, how we were able to do this with the same tools. Why would it's sort of like saying, I could easily do holes in one on a four stroke golf course, but gosh, that 1 foot putt, I'm missing that every time. And it's science, of course, not like sports, but you understand what I'm saying. This is, on the technical difficulty level, this is much easier. Having said that, I also want to point out, even when we build these large samples, like the Pantheon sample, and we look at the residuals in bins, it looks like lambda, if you like lambda, and if you believe it's lambda, the residuals we're seeing are just a couple hundredths of a magnitude. And so how are we messing up 0.2 of a magnitude when we go, over this whole look-back time, and we're not messing up at a couple hundredths of a magnitude? I don't know. There's no telltales of any problem here, I would say. Of course, you always have to look even further back in history on the Hubble constant, right? Of course, everybody knows that the value used to be extremely high, but I ask you to sort of flip this around and remember the Hubble constant has almost always been a bellwether in cosmology, and seeing problems in it has always actually taught us something interesting about the universe. So when the Hubble constant was too high, implying that the age of the universe, the age of the universe was less than the age of the Earth, this was a cosmological problem, right? One of predictions not matching measurements, much like what we had ours. People were calibrating one as their distance indicator and then seeing the other one far out and not realizing those were different generations. That is new physics, new astrophysics, and that's very important. It's not something to just say, you're making experimental errors. In the 1990s, the Hubble constant, even though people argued hard in this range of 60 to 85, thinking that omega matter was 1, still gave us a universe about 10 billion years old, another cosmological problem. Why? Well, dark energy. The omega matter was not 1. That changed this calibration. So this, smells a little bit like the past in that way, in the 2010s, that we see the Hubble constant. It's higher, again, than a cosmological expectation. I don't know what, if anything, we will find, but this route has often taught us something interesting about the universe. So last point I want to make, which is we've been saying for a long time now that we know exactly how old the universe is, but I have to question, do we really? When we say we know exactly how old the universe is, we usually start with very precise CMB data. We use vanilla lambda CDM, and of course that tells us not only what the Hubble constant is today, but it also tells us exactly what the age of the universe is. But if there's an issue here, and of course I remind you that T naught is very closely related to 1 over H naught, there's just order 1% correction to that. If we get a different value for the Hubble constant, we have to be open to the possibility that the universe could be 1 billion years younger, in which case it's kind of funny to keep going around saying the universe is exactly 13.8 plus or minus 0.02 billion years old unless it's not. Because, this exact same, as I said, that exact same machinery that is telling you precisely that age is the exact same thing that's in, 5 or so sigma tension. So I don't know what the answer is to the age of the universe. I'm starting to feel bad when we go around quoting it to such high precision if we have this big question. Anyway, that's it. I will end there, and happy to take any other questions that you have.
How significant are the errors due to gravitational lensing in your detection of light?
Which measurements are you talking? Oh, they're very minimal because we're not out very far. Where you mean just weak lensing? They're very. That's a very small effect. We're not even going to high redshift. We're doing this really at redshift 0.05, 0.1. So it's negligible, not even 1%.
In this these holy cow measurements you mentioned, so I gather this is based on measurements of quasars.
Quasars, time delay. So they monitor 4 images of quasar with very high cadence, and they're able to measure a 3.24 day delay between image 1 and image 4. That plus the distorted image allows them to actually model the positions of the masses, and then eventually relate those to differences in distance that light has to travel, and then eventually a Hubble constant.
And does the accuracy increase with the number of images that they
I don't think so. I don't think it increased. I don't know. Actually, I don't know that well. I'm not sure.
Can you comment on the where in the sky, how isotropic the supernovae you use?
There's been a couple of good papers on that recently showing the isotropy. You could look, there was one from Dragan-Hutterer, and I can't remember who the other author was, but where they looked at that issue in particular, and it's quite isotropic, and it puts pretty strong constraints on the isotropy of expansion.
Yep, please.
Should we worry that we don't know what type 1A supernova progenitors are?
Yes and no. We should worry, wearing your astrophysicist hat, you should worry, because we would like to understand that. We'd like to understand, whether they're more common double degenerates or single degenerates, issues of nucleosynthesis that occur as a result. As cosmologists, you should not worry very much, because The calibrations are all done empirically. If you told me the answer right now, whether it's more this one or that one, I wouldn't change the way we do the calculations. So I think that we calibrate them empirically based on their light curve shapes and environments in some cases, but not with knowledge of their progenitor type. They're a population that starts out with a very narrow distribution of luminosity, and we narrow it further empirically.
Any further questions or comments? Please.
You said that none of the single effects like the local void, any of these effects like with a bit of a local void change, a bit higher effective.
Yeah, but usually we just call that being really unlucky, right? When there's, I mean, if you're going to say, hey, it doesn't have to be a 9% effect, it'd be like 10.9% effects, and then we go, gosh, why did they all go in the same direction?
Okay.
And they were unrelated. So, so part of my answer here, do I say it? Yeah, right here is, this bullet. If not a conspiracy of errors, it could be a conspiracy of errors. That's what a conspiracy is. In this context, is things that would seem to have no reason to know about each other or anything, and they keep going in the same direction.
Okay, well, if there are no further questions or comments, let's